Honestly, I don't like doing diprotic acids. I just put that on there because I want y'all to be exposed before you go to see Dr. Hauser. All right. So, or Dr. Blauk in 220. So the question is, what is the H plus of a 2.00 molar solution of 2,6-dinitrobenzoic acid? And I'm giving you the Ka. Okay. All right. So the Ka is 7.9 times 10 to the negative 2. Okay. So here's the deal. What I've done is I have an acid. We are solving for the H plus. I've given you the initial concentration of HA, and I have given you the Ka. And so this is a problem because I've given you an initial concentration and I've given you the equilibrium constant. You're going to have to solve for X. Okay. Oh, I got a chatsy. Oh, okay. All right, cool. Gotcha. All right, so what we're going to do here is we are going to go. Now, here's the deal with acids, y'all. Bases sometimes get a little more complicated because if you have a base dissociate and give off two OH minuses, but our weak acids, it's always going to be the same reaction with the same format every single time. So the acid and the conjugate base are going to be different, but it's always going to follow the same basic formula, all right? HA dissociates to make H plus and A minus. That is always going to be our R for every single weak acid reaction, okay? So we start off with our initial. We start off with 2.00 molar of HA, okay? We have 0 H plus and 0 H minus because we assume when we start our reaction, nothing has happened yet, okay? So then we are going to undergo some change where we subtract some amount X and we convert it into H plus and to A minus. Now, why is it minus X and then plus X on the right? Because initially, if we solve for our Q at initial, we would have 0 squared over 2, and that gives us 0. And that is less than our Ka of 7.9 times 10 to the negative 2. So we are going to have to take reactants and make products to approach our equilibrium constant. In theory, I could give you all products and you have to go the other way, but that's not what we're doing here, okay? So, and then why is it just minus X and plus X? Why not 2X, why not 3X? Because we have a 1 in front of all of our as a coefficient in front of all of our components, so it's just minus X and plus X. And that finally brings us to equilibrium. So at equilibrium, for HA, we start off with 2 molar. We subtract some amount X, and that is what we have at equilibrium. We have X of H plus, and then also X of H minus, because X amount of our HA is dissociating and making equal amounts of our plus and our minus. Now, every acid has the same expression for Ka, okay? At least that we are going to be using in this class, because we're going to focus on one ionization at a time, all right? So it is going to be H plus times A minus over HA, all right? So if we solve in, we get X times X over 2.00 minus X gives us Ka. Now, y'all, here's the fun part. I told you the Ka. We know that it is 7.9 times 10 to the minus 2. So what we can do is we can solve for X. Now, in theory, we would just go and we would turn it into a quadratic and solve for X. However, we're going to make a simplification. And we're going to drop the X in the denominator. And we're going to see if we can do that. If we drop the X, what we get is we get X squared is equal to 2 times 7.9 times 10 to the negative 2. To get rid of the square, we take the square root of both sides, and we get X is equal to 2 times 7.9 e to the negative 2. We take the square root of that, and we get 0.397 molar. Now, so here's the fun part. Because we said, oh, we can drop the X. I don't know if we can drop the x. And Jordan's shaking his head no, and Jordan is correct. Because if we go and we take 0.397 and we divide it by 2.00 molar, and we get, and then we multiply it by 100, we get, I don't know what it is off the top of my head, but it's about 20%. We can only drop the x if it's less than 5%. Yeah, okay, yeah. So it's less than 5%. So we could go through, so what we're going to have to do is you're going to have to go back and multiply everything and get x squared plus 7.9 times 10 to the negative 2x minus whatever 2 minus 2 times 7.9 times 10 to the negative 2, all right? Now we could go through and we could plug it in. We're not going to do that, all right? Because we have a limited amount of time. I got somewhere to be and y'all got stuff to do too. So if we go in though and we solve for our roots, if we do minus b plus or minus the square root of b squared minus 4ac all over 2a, we get that x is equal to 0.361 molar. All right? I'm not quite sure if that's 100% right off the top of my head, but we're going to go with it. Because okay, Jordan's giving me a thumbs up. All right, I'm trusting you. And I know that Adam did it out the whole way in his breakout room too, and this is the answer that's on the slide, so I am trusting it because I trust y'all. All right? So, what that means is this is our x. So that means that at equilibrium, we have 0.361 molar of A minus, we have 0.361 molar of H plus, and our HE is equal to 2 minus 0.361 molar. So we now have what we need to find our pH, all right? So our pH is equal to negative log of 0.361. And that's going to be high. All right, so negative log, or a really low pH, quite acidic. All right, if we take the negative log, that is, okay, so we have a pH of 0.442. That's pretty daggone low, all right? But either way, that is our pH. All right, so how do we know if this is right? What we can do is we sub in our expressions into our equilibrium constant, or into an equilibrium expression, and we see if they give us our Ka. Oh, Jordan, you're raising your hand. What's up?
Yeah, didn't we already find H plus since we found X?
Yes. Yep. But what we want to do is we want to check to make sure our answer is right. And the way we can do that is we go and we take our equilibrium expression and we say, okay, 0.361 squared over 2 minus 0.361. This is how we're going to check to see if we got the right answer. All right? So this is the check built in. So 0.361 squared divided by 2 minus 0.361. 0.795. Yep. We're good. We get 7.95 times 10 to the negative 2. All right? We're close enough. We got it. We're good to go. Woo! Pat on the back. Okay. All right. I'm going to stop recording that.